So today,
Good question.
oh, yeah, go ahead.
Do you think the whole course finally is going to be online?
To be honest, I have no idea. I can tell you currently the plan is to go back to in-person by January 28th. By week 5, hopefully we'll be back in person, which would mean that yeah, the rest of the course will be online, or sorry, in person. If it were to extend, I think at least for this course, the projects themselves, it's not too problematic to do online, and that's what we did last year. So it's a final project presentation, so everyone will just take turns presenting online.
Okay.
But hopefully we'll be back in person in a couple of weeks. So today we'll be talking about non-fossil fuel energy sources. So last class we talked about coal, natural gas, a little bit of petroleum, but we'll cover that actually tomorrow when we talk about transportation. These are mainly going to be for non-mobile sources. So specifically for electricity generation, last time we had looked at this figure already. This is just a sort of quick refresher, and today we'll be focusing on some of the hydro resources, nuclear resources, solar and wind. And you can see that the distribution of these sorts of resources are going to be quite different from some of the fossil fuel sources that we were looking at last time. So again, another sort of repeat from last time, looking at capacity installation of new power plants over the last century or so. And we'll first focus looking specifically at nuclear generation. And again, you can see that the vast majority of nuclear power plants was installed during the 70s and 80s. And so this has important implications in terms of moving forward from sort of the modern era, particularly because a lot of these plants typically have around a 40-year lifetime, which means that around now is actually when you're seeing a lot of decisions being made about whether or not to keep these nuclear power plants going. And so essentially what you have to do is decide whether you will upgrade and retrofit a lot of the nuclear plants to extend their lifetime and keep them operating. And that can be an expensive proposition and is dependent on a whole lot of factors that we'll talk about. So unlike combustion, nuclear reactions or nuclear reactors get their energy through a different sort of chemical process. So this is known as nuclear fission. So this actually changes the atomic structure where you essentially bombard this isotope of uranium, so it's uranium-235, with neutrons. And essentially what this does is it splits the uranium into barium and krypton, and it releases a tremendous amount of energy as well as 3 extra neutrons. And so the whole idea here is that you can see that these neutrons are needed in the initial reaction, and so this causes sort of this chain reaction where it'll continue to split sort of more and more uranium isotope and release this energy. So it's tremendously energy dense, which means that you can produce a whole lot of energy from even a small amount of your initial resource. So 1 kilogram of uranium can produce 24 gigawatt hours of energy. So that's several million times more energy dense than coal. If you'll remember back to the first lecture, the sort of 1 kilogram of coal releases about 30 megajoules of energy. So this is like on a completely different scale. I will note that this chemical reaction here is representing the typical sort of fission reaction. There is a different type of reaction that you can do called nuclear fusion, where instead of splitting an atom apart, it actually combines atoms together. So that's what we refer to in nuclear fusion. That process has not sort of been successfully demonstrated in a way that they could capture in sort of a nuclear plant. It's not like commercially viable. Instances of nuclear fusion are only taking place sort of at the laboratory scale. And so there are sort of a lot of technical challenges and hurdles to overcome before that can be sort of implemented into practical needs. So in terms of resource availability, sort of total resource availability on Earth is somewhere on the order of several megatons, so 3.5 to 6 megatons. And as I mentioned before, these sort of reserve and resource numbers are sort of subject to change if more of the resources found or better extraction techniques become available. It takes about 27 tons of raw uranium fuel for a 1 gigawatt reactor to use over the course of a year. Okay, so the way a nuclear plant works is actually very similar to a coal plant. So it uses a steam turbine. And in fact, if we were to look specifically at everything sort of to the right-hand side, so your reservoir of water going into getting heated up, producing steam, going through the turbine, passing through a condenser and going back into the reservoir. This whole portion is exactly the same as a coal plant, right? The only difference is that the thing that it's heating up the initial reservoir of water is not through combustion of steam. It is being done. It is capturing heat coming from the nuclear reactions here. And again, you'll notice that there is a closed loop for this reactor of water. And so in this case, this particular closed loop is probably a little bit more obvious why you want something like this. The water in this reactor is actually going to be very radioactive, and so you wouldn't want to have that going through your turbine or exposed into other like equipment. The nuclear reactions, so I mentioned that it undergoes this sort of chain reaction, but it is sort of well maintained, so it's like a controlled chain reaction, and they they have some pretty sophisticated ways of ensuring, right, that you're not going to have things like nuclear meltdowns, where your nuclear reactions sort of become uncontrolled and can sort of damage the reactor or potentially damage larger parts of the facility. It's not really possible anymore for uncontrolled sort of reaction where you lead to an explosion that is somewhat of a unfounded fear regarding nuclear plants and safety, which we'll talk about a little bit more. The other sort of substantial difference with the coal plant you'll notice is that in these in the reactor portion of it, you are not undergoing combustion, which releases a whole bunch of byproducts. And that means that that you don't have the long exhaust pipes, right, coming out, because there are no sort of emissions coming from a nuclear plant. So from an environmental perspective of emissions coming from a plant, this is sort of as clean as it comes. There are other issues regarding, nuclear waste, which affect the sustainability of these things, but at least from an emissions perspective, these are sort of as clean as a sort of traditional renewable plant. Okay, so I was talking about retirement of nuclear power plants, after they reach their sort of 40 to 50 year time limit. And so this is a graph here where we can see license expiration dates for currently operating US nuclear reactors. Some of them have are operating right now without license renewals, but have submitted applications for renewals. And so those are all of these guys in the dark brown, which will sort of, once those licenses are applied, then they'll turn green, right? And so they'll be able to operate. And so a lot of existing reactors have already been granted license renewals, which is why you see so much green. And that often means that they have to undergo some of these like retrofits and upgrades that I was talking about. And that may extend the life anywhere from 10 to 20 years. So in another 10 to 20 years, we can see a lot of the nuclear plants will start to expire their license again. And I actually don't know if you're able to keep doing that, but it'll be an interesting time as more and more nuclear power will either be forced to retrofit and upgrade again if they're allowed to, or to retire. And then there are reactors that are intending to just go ahead and shut down, and so those are the ones in these sort of lighter colors. And so there's definitely been a decline in nuclear power over the last decade or so. And there are a couple of reasons for this. Very high capital costs. And so when we think about installation of new plants, a lot of these have actually been unsuccessful because of this reason. They'll actually go into the initial stages of construction and deployment, but for a variety of reasons, they could just run out of money. A lot of those projects end up bankrupt. There is pretty strong NIMBY opposition, and so NIMBY stands for not in my backyard. And that has sort of led to a lot of popular protest to the construction of nuclear power in specific areas. So you can imagine, even if you were a proponent of nuclear power, like, would you want someone to be building a nuclear power plant, next to where you live? There's a lot of hesitancy that drives that drives sort of activism against the construction in certain areas. Specifically in the United States, nuclear power is really difficult to certify. And so it requires lots of certifications and licenses, and this can sort of drag out the process, which means that you have to spend more and more money in its construction. There are, in terms of sustainability and thinking about sort of environmental aspects, there are a lot of compelling alternatives in wind and solar. Because of the scalability of wind and solar, oftentimes it's just a lot easier to build, for example, smaller amounts of capacity. You can imagine that for a nuclear plant, you want to keep it operating sort of all the time, and you wouldn't necessarily want to build like a sort of small version of nuclear. Although I will point out that there is a technology called small modular nuclear reactors, which are these like essentially small versions of nuclear reactors that are actually portable and can be moved around. There isn't a whole lot of that sort of in practice right now, but it's something that some people have discussed and talked about in certain circles. And then lastly, sort of the big disaster factor, right? So Fukushima happened in sort of the modern era for energy, and it sort of stokes a lot of the fears that people have about nuclear power. I will say that in comparison to sort of other fossil energy, and actually in comparison to sort of almost any electricity production, nuclear power is statistically like far and away the sort of safest in terms of the pure number of injuries and deaths related to it on a energy produced basis. And that's because of sort of the strict safety measures that a lot of nuclear power plants have to take. And so you are much more likely to die, for example, if you are someone who works at a coal plant compared to someone who works at a nuclear plant. And then in terms of things like radiation safety, actually the sort of lowest sort of background radiation place that you could be in the whole world is probably inside of a nuclear plant, because they put so much like radiation shielding. Background radiation is actually lower in most nuclear plants. Yeah, okay, so I see a question here. So most safe per unit of energy. Yeah, so what that means is like per, say, megawatt hour or gigawatt hour of energy produced by a specific power plant, the number of injuries and deaths per that amount of energy produced is lowest for nuclear power plants. So hopefully that makes sense.
Yeah, I was asking because I could imagine that maybe a solar, a utility scale solar plant would be safer, but it's less energy intensive than a nuclear power plant, right?
So there are some injuries that happen at like at the at solar plants. I guess I'm not exactly sure, but I'm guessing it happens like during the installation and construction of the plant, and even sort of over the lifetime and all the energy produced, nuclear ends up being lower.
Quick question.
Yep.
So you mentioned how radiation inside of the plant is actually extremely low because of all the shielding.
Yep.
Have we tracked that in any certain measure and maybe tracked employees and instances of cancer later on or
Yep.
anything like that?
Yeah, exactly. That's actually exactly what they do. They have to track it sort of on site and sort of and onward. So anyone who works at a nuclear plant, I would guess in specific areas of a nuclear plant, has to have this sort of radiation monitor on you sort of at all times, and it has to be below a pretty low threshold. Actually, that's actually how they, and they also have background sensors in those areas, and that's actually how they know how much radiation that people are exposed to who work at nuclear plants. And then we know that actually sort of background environmental levels are higher because you can have sensors and readings from sort of other researchers sort of outside naturally. Yeah, and so cancer rates for nuclear workers, I believe, is not statistically lower sort of than your background population, but it's not different.
Thank you. That's actually really cool.
Yep. Yeah, exactly. So Duncan's pointing out all employees wear radiation badges. So this applies to if you work in certain academic labs. Yeah, I'm actually an affiliate at Lawrence Berkeley National Lab, and we have to do all this like radiation training because there's certain parts of certain buildings where like if you go through, you have to wear these radiation badges. I've never had to do that, even though I go on site sometimes because I don't go into those areas, but we have to do trainings all the time for it. And if you're working at a nuclear power plant, I'm sure that the training for radiation stuff is a lot more robust. Yeah, any other questions? Okay, and so we will move on to talking about renewable energy. So definition of renewable energy. So this is energy that's derived directly or indirectly from either energy of the sun or of the earth. And obviously it has to be renewable in the sense that unlike sort of every other fuel that we've talked about before, which is a resource that will eventually get used up. So all fossil fuels and even nuclear, you are using up some of that product to generate the energy. And in this case, you're doing the same thing, but that energy is sort of continuous and will come back, right? Or technically, like, yeah, the sun is going to like explode in a couple billion years, but we essentially consider it to be an infinite source of energy. So these are your 6 types of renewable energy. You've got solar, wind, biomass, hydropower, ocean, and geothermal. So why are renewables important? Why have we been sort of pursuing this? It's a key component of sustainability and securing our energy future, right? We're not going to be using up that resource like we will with other types of fuels. Renewables are also an important strategy for energy security. And so for a particular country, let's say the United States, we don't want to, or the government doesn't want to rely on other countries for their resources. So having to, say, import oil from Canada and Mexico, or sort of back before we had shale, doing imports of natural gas from Europe. So a lot of these issues in terms of geopolitics are reduced a lot when you can simply produce the energy yourself. As we sort of saw in new capacity installations, renewable energy is expanding very rapidly. Into 2019, it accounted for almost over 70% of new worldwide capacity. And that's predominantly wind, but there's some solar in there, and we'll see more sort of specific numbers in a bit. As I mentioned, non-depletable, widely available, which is an important aspect of it. The sort of distribution of fossil fuels definitely tends to favor certain countries, right? We think about places like for oil, places in the Middle East and in Africa, some places in South America. When we think about like coal and natural gas, the US has a lot of those resources. And so that sort of concentrates a lot of the power for who controls that resources in certain places. But for solar, right, that's available, and for wind, it's a lot more sort of widely available in many geographies. The main reason why we had not seen a sort of wide-scale deployment of these resources is probably having to do with cost, and some sort of technological limitations, but now they're becoming increasingly economically competitive. And so if we think about the cost to build like wind on a per energy basis, it's now sort of low enough that it can compete sort of directly with something like a natural gas plant. And obviously there's issues related to the emissions, particularly greenhouse gas emissions for fossil fuel combustion. And this is something that renewable energy can avoid in most of the versions of renewable energy. Generally, they're going to be higher costs, although again, those costs have come down over time. We think of wind and solar as being sort of totally clean, but they're not actually always 100% carbon neutral. And so we'll talk about some examples of that, of non-carbon neutral renewables. And then depending on the type of renewable resource, the land use, water use, and materials use can be fairly significant. Integrating renewables into existing energy systems can be challenging. So, okay, so what does that mean? You know, the sun doesn't always shine, the wind doesn't always blow, and so in order for you to sort of adequately be able to meet electricity load, there has to be some other sort of mechanism to get electricity to you when the sun isn't shining or the wind isn't blowing. Okay, so question here, does higher cost mean establishment cost or cost of running the plant? So if we think about solar and wind, it generally means the capital cost. the cost of production of sort of a new unit of energy once you have a solar plant or a solar or wind plant installed is zero, because you don't have to pay for your sun resources or for your wind resource like you would for you know, a kilogram of uranium or for some amount of coal or natural gas. So on the sort of per margin side, it's going to be way cheaper actually. But the issue is that when we think about the economics, you have to sort of integrate the whole sort of life cycle of that plant, and when you do that, you can compare, for example, over the entire lifetime of the plant in a metric called like a levelized cost of energy or electricity, and those costs will end up being higher for renewables than for a lot of fossil plants. We're actually going to look at specifically how you go about calculating those sorts of numbers and how you do sort of like benefit cost analysis and economic analysis in a later lecture. Okay. So growth in renewable capacity. So this is a chart kind of similar to that capacity install chart that I'd shown before, but this actually shows sort of the cumulative capacity over time over the last sort of 2 decades. And we can see sort of right at the start, the vast majority and still the majority of installed capacity is with hydropower. That's definitely probably the sort of cheapest and sort of oldest to be in place already. But unfortunately, hydropower resources, there's a limit to essentially how much you can install, right? Because it depends on the availability of resources that can be dammed. So in the US, for example, there is very little sort of spare hydro capacity that hasn't already been deployed. There are actually very few sort of rivers, sort of larger scale rivers in the United States that don't have that don't have hydropower sort of taking advantage of that resource. You can see sort of the largest growth over the last 2 decades being mainly in sort of the wind resource, and sort of more recently solar resources are starting to catch up. Okay, where are renewable energy investments happening? We can see, so this gives some sense of, you know, how much different countries and areas are investing into these resources. And so this is sort of across all renewable energy, including both wind and solar. And in the US, for example, there is a substantial amount, but the trends in I would say in China in particular, and to some extent other portions of Asia have been growing to a much larger extent than in the US. And currently, you know, China is actually putting in sort of a fairly sort of absurd amount of renewables every year. And so there's definitely a lot of movement by many different stakeholders to invest in these sorts of resources. Okay, top renewables by technology. This is sort of a breakdown. We can see for hydro, hydro is going to be pretty dependent on what resources are available, as I'd mentioned before. But for solar and wind, and for CSP, which is another form of solar power, which we'll talk about, we can see sort of the typical actors that you would expect. So China, the big one, US, some parts in Asia and Europe. A lot of the countries that have sort of stronger economies are able to invest in some of the higher costs related to these renewable generation resources. Yeah, so CSP is concentrated solar power, and it is a different form of solar that you can capture sunlight energy with. And we'll talk about exactly what that entails later on today. Percentage of electricity generated by renewables. So we can see fairly low or relatively low for the US over here. So this is back a couple of years ago. The number is definitely higher now, but in 2015, we were at almost 13%. What the sort of thing that you should pay attention to for a lot of these countries that are producing more than, say, 50% renewables is that the vast majority of that is coming from hydropower. And so again, that's a sort of highly resource dependent, resource availability dependent form of renewable energy, right? You can only use it if you have like resources that can deploy hydropower. And so if you take the blue away, the numbers will look quite a bit different, right? The sort of big standout is in so in parts of Europe where you have high sort of offshore resources for wind, places like Denmark, Portugal, Spain, those areas are able to capture a lot more of that wind resource. Actually onshore too in Denmark. So we've shown a slide of this before, but this is looking specifically at the US just as a quick refresher, the breakdown of renewable energy production and consumption. So this is energy production and consumption and not electricity. And so you actually have a relatively high portion of biomass. This is something that we'll talk about way later in class, but this actually refers to, a lot of this is having to do with ethanol being produced from biomass that ends up sort of getting blended in gasoline. And so I believe that's where most of this sort of energy production refers to. But when we think about electricity, that's going to be mainly these guys, a little bit of biomass, but mainly this half over here. Okay, so any questions about sort of our high level overview of renewable statistics? Okay, so we'll dive in and talk specifically about each of the technologies, starting with So hydropower has been around for quite a long time. And this is one of the most sort of steady forms of renewable generation. And then in terms of sheer capacity, we're able to get quite a large amount of this resource, even in the United States. So back in 2010, if we looked at the historical install of hydroelectric generators, you know, there's sort of a large growth in the 50s and then sort of slowing down and tapering out in the 90s. And again, this is simply due to the fact that we sort of used up or installed this particular form of renewable generation at all the sort of available sites in the country. So you'd be pretty hard pressed to get a substantially larger amount of hydro in the US. So global hydropower potential. So the annual runoff in sort of their metric is meters of water. So as you get more and more sort of red, that refers to locations that receive sort of more, it's a combination of both getting more rainfall and having some sort of elevation differences that you can take advantage of. And so in the US, we are particularly, we have particularly rich resources in the sort of northwest of the country. So the Pacific Northwest is pretty famous for having a lot of hydropower use. And you can see sort of other places around the world which are able to employ hydropower. And it's usually going to relate to, again, places lots of rainfall and sort of more mountainous regions.
I have a quick question, Alan.
Yeah, sure.
This general statistical like conglomeration of hydro resources does not include tidal, correct? Like tidal power is its own thing.
Yes,
Okay.
yes. Tidal power is its own thing. Yeah, I don't think we're going to be talking about tidal power in these slides. I might have one slide on it, but so speaking specifically about hydropower. So to avoid any confusion, I think the blue dots that are like in the middle of the ocean, those are all like islands, and so they're making sure to capture to capture that on the map. But for tidal power, this refers to the ability to capture power from sort of moving waves and that sort of thing. So generally, what I will say about that is that tidal power as a technology is pretty new. The efficiency of being able to capture energy from tidal power is really, really low. And that makes all the sort of economics of tidal power to be totally sort of unfeasible to install any sort of tidal power at a large scale. And unfortunately, the amount of energy that you'd be getting from tidal power is just sort of at this point too low to be considered a sort of viable resource. So theoretical hydropower is the sort of theoretical maximum energy carried by water runoff. So that the theoretical is estimated to be between 16,000 to 40,000 terawatt hours. And so this thinks about elevation, precipitation, and topography. yeah, and a lot of that theoretical potential, it's like the same type of thing as being able to capture all of the sunlight. You can't do it for a number of reasons, the inaccessibility of getting the flow and other sort of siting issues. So one important issue related to hydropower is that reservoir levels are affected by precipitation, and this is going to vary quite a bit over the course of the year. And so this is, for example, like a typical year of precipitation in San Francisco. Okay, and so you can imagine that your use of hydropower is going to be sort of higher in seasons sort of following precipitation, and then lower where you have sort of less precipitation available. And this actually, it's not only the sort of availability of water per se as like something that you have to like pass through the turbine. We'll show how that works in just a second, but also it's related to the amount of energy that you could produce out of the turbine is related to the height the water in the reservoir, because it uses potential energy the amount of energy is related to the potential energy of the water in your reservoir. And so not only do these change over the course of 1 year, it also is affected across many years. And so if you have been a resident of California over the last decade, you'll know that there have been sort of substantial issues with drought in California, and that can affect the availability of hydro resources. Places that have a lot more steady rainfall, so that will be thinking about places like the Pacific Northwest, that will have substantially higher certainty in terms of the resource availability. So the way a hydropower facility works looks something like this, where you have water essentially passing through this structure here. And so you have an intake flow of water that goes through a turbine, right? Again, it's all about getting something to spin. In this case, we have a hydro turbine, a water turbine, which instead of passing steam or hot gas through, it is passing water that is essentially being pressured to flow through due to the potential energy difference in the height in the reservoir versus what's sort of coming out of your hydro facility. And so by spinning this turbine, you can power the generator and produce electricity. The amount of power that you can extract from a hydropower plant is a function of the turbine efficiency, a function of the density of water, which really is not going to change that much. It will be affected by like temperature of your environment, but it's not like they're like heating or cooling the water down in any way explicitly. Gravitational constants. And so actually, if you look at this equation, it's closely related to the equation for potential energy, which is mgh, but this is over time, right? Because you have a flow rate. So this will calculate actually the power from rather than energy. And then the H stands for the head in meters, and this is the difference in height between water coming in and then water sort of going out. So between the inlet and outlet. So actually, if I go back one slide, that refers to the potential energy difference at your intake versus your coming out of this turbine here.
Excuse me, Alan.
Yep.
Can you go back to the equation?
Sure.
Because that equation, I guess, is coming from the first law of Newton, right? No, the acceleration thing, right? Because so you can measure that just when you have an height.
Yeah, so it comes from
Like where do you use that? Because you have there the density and as the acceleration, I guess it's because you're considering.
So this equation comes from the equation for potential energy, which is equal to mgh. So this is mass, gravitational constant, and then height. So for any object, like say I took a bowling ball, right? That's the classic physics example. And I sort of put it on top of a building that was say 100 feet high. So the amount of potential energy that bowling ball has compared to a bowling ball that was just sort of sitting on the ground, all the energy that you could possibly extract from that would be related to the height. So, 100 feet times its mass times its gravitational constant. So this is actually exactly this equation, right? So we're calculating the mass of water, let's see, based on the density versus a volume here. So that gives you your kilograms. And then because that, right, so that bowling ball at the top of the building versus at the bottom of the building, you can't actually capture all of that energy. And so the amount that you can capture is based off this constant here.
Efficiency.
Rho, yeah, the efficiency. So you have your gravitational constants, and then you have your height here for your head. So the main difference is that you have a per second. So energy per unit of time is equal to power. So to go from potential energy into power, we need to divide by some time, and so that's by the flow rate. So this calculation of power from hydro power plants is quite literally sort of just a version of your potential energy equation.
Yeah, it's a second law of Newton. It's very interesting to calculate that.
Okay. Last bit about hydropower. So you have your different types of turbines. We're not going to go into any of the mechanics or specifics about these turbines, but the idea here is that actually there are turbines that are sort of designed for particular applications, and so sort of on the right hand side we can see sort of how this works. So the flow, the combination of the flow and the sort of head, so that the height differential can lead to the use of turbines that are optimized for particular combinations of these two parameters. And so at sort of low flow, lower head, you might use like a Kaplan turbine, but then for applications that have a particularly large height difference, you might use Pelton turbines, and then ones that have sort of both that are high, you might use these sort of Francis turbines. So there are sort of specific designs for these of turbines for hydropower resources. Okay, any questions about hydropower before we move on? So why don't we actually, this is a good spot to take a quick breather. So let's do a 5-minute break here. And we'll reconvene at 11:02. And again, I'll stick around in case anyone has any questions. Okay, let's get back into it. So next technology we'll be talking about is wind power resources. Okay, so again, I know that we haven't talked about levelized costs or anything like that. but think of this as kind of some way of measuring the sort of lifetime cost of building and using a particular resource. So for wind, that cost has drastically declined over the last 40 years. And so in the 80s, a sort of typical sort of install could be on the order of 50 cents per kilowatt hour. And that has since sort of fallen by tenfold, or an entire order of magnitude, right? Decline. So we're talking more on the order of 3, 4, 5 cents per kilowatt hour today. And as a result, that has put wind sort of directly into competition with the cheapest sources of production. So on a levelized cost basis, wind is as competitive, if not more competitive, than even natural gas today, which we have sort of considered to be, some of the cheapest resource over the last, say 20, 30 years. And as a result, you can see that the capacity growth has been very sort of substantial. So we're talking about on the order of only, say, 4,000, so 4 gigawatt installed in 2000, sort of now edging closer to 100,000 megawatts or 100 gigawatt install just in the United States. So similar to the hydro resource, we can see where the availability of wind is the highest. So this is based off of wind speed at 100 meters high, and sort of purple and blue is the highest. So on land in the United States, you can see that sort of the Midwest area has the highest availability of resources for wind.
Alan, excuse me.
Yes.
So when you mean, how do you measure the quality of the wind? Is it because it's constant or is it because it's strong?
Yeah, so this is a combination of both, because this measures the average wind speed. So the continuity of wind is fairly important, right? It's the same kind of principle for solar, like whenever the sun is shining. But for a lot of these wind resources, it is going to be fairly continuous. So the thing to think about here is not that the wind disappears, it's that the speed will actually slow down in certain hours. So if you have like a really good large wind farm, typically what ends up happening is that it never really drops down to zero. It may go from, full capacities down to 50% capacity, 40, 30% capacity. So the continuity is important in the power production for sure. But the energy that you're going to be extracting is just based off of the wind speed, and that's what's going to be sort of fluctuating.
Because I don't know, maybe I'm wrong, but every time I see a windmill, even if the wind speed is high, they are going slow. So it seems like they don't really need a lot of like a high speed. It's more like the constant.
We will, so similar to the equation that I showed you for hydropower, we're going to see exactly how wind is captured, how much energy that you can extract. And one of the important terms there is actually wind speed. So we'll see, and I'll sort of explain the logic behind that. Okay. there are also offshore resources. And so that refers to wind turbines that are built, well, literally offshore, so in the water. And you can see that as soon as you're over the water, right, you can have a pretty absurd amount of wind happening, relative, right, to what's sort of on land. And so blue, red are sort of by far the highest resources. So right here in the sort of Pacific Northwest and Northern California area, you've got a large amount, and then quite a bit in the New England offshore area. But again, you have some opposition to people building wind turbines there, like the same sort of NIMBY idea as for nuclear. Okay, so quick back of the envelope. Let's say a good wind resource, 500 watts per meter squared, and the meter squared is the rotor area at 7.5 meters per second. So this is something like 17 miles per hour. We can convert that for efficiency, and we end up getting something like 1,000 kilowatt hours per meter squared per year. And so this would be, you know, a good sort of wind resource. So the size of the rotor to power a conventional house might be something like 24 meters squared. So this would be a 5.5 meter rotor diameter. To power a car, similar type of size. And you can think about, you know, if you had a typical wind farm spacing, sort of the way that you would space them out is about 5 by 10 diameters, and so that refers to kind of the spacing in between each of your turbines. And we'll see sort of how this is going to play out in just a second. So this is a sort of diagram of what a wind turbine looks like. So you've got, it's right, fairly straightforward, but same idea here. As long as we can get something to spin, then we can extract energy out of it and produce electricity. So in this case, the turbine is this whole sort of structure itself, spinning the rotor blade. It'll go through this gearbox, right? And so oftentimes it may look like a wind turbine is spinning fairly slowly because of the size of the large blades, right? But think about the sort of mass that it's moving, and think about, you know, from like a gear ratio perspective, the size of essentially the super large gear. And so this goes through this gearbox sort of thing. It's kind of like a transmission type of thing for a vehicle, and that would go through and power this generator. And these will go through eventually down this tower into a transformer before it goes into your sort of main electricity grid. These things are crazy big these days. Yeah, if you've ever been to a wind farm and sort of stood next to these, you can really sort of appreciate how large these are. And gain some appreciation for like maintenance workers who have to climb the inside of these towers. They have these like series of ladders that go up. Those guys get a lot of exercise because they have to climb quite a bit every day to sort of fix broken turbines and do maintenance and that sort of thing. Okay, so the average efficiency is 35 to 45%. We'll see how that plays into the equation in just a second. And the reason why these are so high is for two things. One, you actually have to have a certain height to clear for the blade. And then wind tends to be higher at sort of higher elevations. And so capturing things at like 100 meters high is going to be way better in terms of power production because wind speed is higher at those elevations. Oh, okay, yes. I totally missed this. I'm sorry, I wasn't looking at chat. There's a question about whether or not there's a price difference between offshore and onshore wind electricity. Yes, there definitely is. You can imagine that the cost of like trying to install like one of these big towers in the middle of the ocean is going to be really different compared to sort of installing it on land. And the size of these things are actually typically way larger for a lot of the offshore wind turbines, which means lots of materials, or a lot more materials and different sort of construction required. And so the cost of production is very different, which leads to fairly different economics between onshore and offshore. And I think I might have some numbers in later slides, but if not, yeah, there are definitely substantial cost differences between onshore and offshore wind turbines. Sorry, I'll try to keep my eye on the chat a little bit more. Okay, wind energy. For hydropower, we showed how it was related to potential energy. Wind energy is actually the exact, analog. So wind energy is is directly an analog of kinetic energy. So that is 1/2 mv squared. So mass times the velocity. So the idea of kinetic energy, right, is if you have some kind of like moving object, how much energy is in that moving object compared to when it's still. So with the same sort of bowling ball thing, if you were rolling the bowling ball, how much energy could you extract from it by having it come to a complete standstill? So the amount of energy in wind, so the mass, we can translate the mass of wind passing through, this is the volume of air that's passing through the cross-sectional area of your wind turbines. And so if you multiply that volume against the density of air, that tells you the mass of energy, or sorry, mass of air, not energy, mass of air passing through that cross-sectional area. And ultimately you will arrive at this equation. So 1/2 surface area times time, because you need to know that multiplying the wind speed times density times time gives you the mass times velocity cubed, because the velocity squared is part of it, the initial kinetic energy equation, and it gets multiplied one more time by the wind speed. Essentially is the same thing. So this is the energy, the kinetic energy of the wind passing through the turbine, and then you could then multiply this. You could multiply this whole term by efficiency to get the amount of energy that could be feasibly captured. And then if I were to divide this term by time, then it would translate into power. Again, energy over time is equal to power. And that would give you sort of the analog that we showed before for hydropower. But this is essentially how you capture the wind energy.
Alan, but
yes,
can you back a second? So that is going to capture just the potential, right? because as you mentioned, you're not multiplying there for the efficiency of the system plus the transmission to the gears. Well, I would say a gear because it looks like a transmission, right? But the transmission is also it's going to make a big difference.
So, okay, so this is energy of wind. The captured energy would be 1/2 AT rho V cubed times, I think we used okay, well, this would be your efficiency.
So that's eta, right?
Yeah, or I was using eta before, so let's go ahead and do that. That's eta, I think. my Greek is pretty rusty. So this would be captured energy, and then power of wind turbine would then be 1/2 AT rho. Oh, sorry, no. It would be rho V cubed times your efficiency. Okay, and then we had times T above, but then you're dividing by T for power, right? So these cancel out. So this would be your power term for your wind turbine.
So, and then ERA there is capturing all the effect of the transmission and all the loss, right?
No, this is the efficiency of the turbine. So
those the turbine.
Yes, so this is the power of the turbine. So here, this would be strictly speaking, that calculates the efficiency, or this would calculate the power at this point right here. You're gonna have, okay, so technically you'll have some losses here.
Yeah. Or actually also you might have winnings, right?
Sorry, wait, sorry, I'm misspeaking here. Hang on.
Yeah.
So it depends, it really depends on what your term, your efficiency term is referring to. So if this refers to, strictly speaking, just the turbine, that will be some amount. But generally speaking, this term here, when we say average efficiency of a turbine, that includes the efficiency captured here, the efficiency of these, and so it'll be the efficiency, not including the step up from the transformer.
Okay.
So that will include everything specific to the single sort of turbine structure. That is the average efficiency. So whatever like mass of air that we're getting at whatever speed coming through this thing, and you multiply by an efficiency number. If you multiply by this efficiency number, you're getting the energy of the wind, ratio difference to electricity coming out of your turbine.
Okay.
Yeah.
Thank you.
Yeah. You're gonna have, like, realistically, right? It's kind of as you're saying, you have some losses as you step up in the transformer, you have some losses over the transmission lines, and then some more as you step down in voltage, and then going over the distribution lines, and then stepping down again, going into, right, the like, 110 volt plug at your house, right? So, but those losses are fairly negligible in comparison to the initial loss that you get from wind into electricity. So this stuff is the bulk of the losses are happening right here and not here. This is going to be like really small. That's going to be like the gearbox and generator losses are like on the order of a couple percent.
Okay. So then we can use that equation just for comparing that one. We can use that just for comparing, let's say like the potential between regions or among regions.
Yes.
Right.
Yeah, exactly. I would, yeah. Just because we're talking about like the terminology, potential energy and kinetic energy, I would be wary about using the word potential too loosely, but yeah, that's right.
Yeah, I mean like the potential of some specific regions, because you can capture that energy with those specific parameters there.
Yes. Yep, that's right.
Okay. And
this is an important concept, right? So when I'm a developer and I'm deciding to install my my wind turbine at site A versus site B, you better believe that I'm gonna try and get a sort of accurate measure of the wind speed, right? Because wind speed translates directly into energy, which directly translates into the amount of electricity that I can produce and the amount of money that I'm going to be making, right? And so the parameter of wind speed plays sort of directly into the idea of economic calculus that you would do for deciding to install a wind turbine. Growth in turbines will blow you away. So if we look at the size of wind turbines, they have progressively gotten sort of bigger and bigger. And so I don't know if anyone's driven by, I think the closest large wind farm to Davis is in Sweden. If you've gone over the bridge to like Pittsburgh, Antioch area, you can see like this giant wind farm, right? And so these wind turbines are huge. They are, we're talking about blades that are sort of on the order of like the length of a football field. And so these turbines, the onshore turbines are producing, say, a sort of megawatt of power. But the ones sort of out in offshore are actually even bigger and can be on the order of like 3 megawatts. I've even heard about 5 megawatt turbines where, you know, the length of a blade is even larger than a football field. So these things are really, really, really tall and sort of massive in scale. So if we look at sort of the sort of new GE offshore wind turbine, these things are rivaling in height of like the Eiffel Tower, right? So really quite large. As turbines get bigger, their capacity increases, right? That makes sense when we think about that equation, right? It's based off of the cross-sectional area of your blades and the sort of rotor diameter. So these things are growing in terms of capacity, growing in height, growing in diameter for their rotors. And we can see this is progressively happening on the average installs are progressively growing over time as the technology improves. Duncan is making a good point. The wind speed is also really important because it increases as a cubic factor rather than linearly. So you get sort of much better sort of returns to operation as the wind speed goes up. And so you really want to be installing your wind turbines in places that have higher wind speeds. And so that makes, you know, installation in offshore facilities like more and much more compelling. Okay, this is kind of the same sort of chart here, but basically capacity factor is improving over time as well, because we're trying to get places in better sort of wind resource quality. This is sort of a cumulative chart of global wind capacity, and you can see the orange is the sort of new annual additions. And so back in 2018, we were up to 590 gigawatts, and now we've definitely surpassed 600 gigawatts by now. So a substantial amount of capacity being installed. One quick note that I sort of haven't mentioned before that's kind of an important concept is the difference between sort of capacity and power generation and this idea of capacity factor. So if I were to install 100, let's say I was to install 1 gigawatt of nuclear power versus 1 gigawatt capacity of coal power versus 1 gigawatt capacity of wind power. The peak power generation of each of these generation facilities is the same, but the amount of energy that you're going to extract over the course of the year depends on how often that generating facility is operating. And we refer to this as a capacity factor. So a nuclear power plant usually has a capacity factor between 95% and 100%. You do not want to turn off a nuclear power plant because it takes so long for the sort of fission reaction to get started again. And to sort of ramp up, it can take on the order of several days to get up to sort of operating capacity. And for this reason, you can think of a nuclear plant as something that's basically kept on all the time. The only time it's going to shut down is for operations and maintenance, which will happen, you know, every year, but for a sort of small, limited amount of time. And so capacity factors are really high. So for something like a coal plant, it will also have, it may also have a fairly high capacity factor because they want to sort of keep it on as much as possible. These days it's going to be lower because you know, it's getting crowded out by other resources, but traditionally you might expect a coal plant to be between like, or it might be upwards of like 80% capacity factor. So with a wind farm, the capacity factor on average is going to be closer to between 30% and 40% for a really good wind farm. And that's because the wind isn't always blowing at the sort of most optimal speeds, right? And so you'll have fluctuations with power production. And in some cases, like the wind may stop blowing for some small amount of time. And so when I say, you know, a 1 gigawatt installation of each of these three resources, the nuclear power generation is going to be the most sort of quote unquote valuable. And so this is going to play an important role in your economic calculations as well, right? Because the return is based off of how much electricity you produce. And so for a nuclear power plant, you know, if it costs $1 to install, you may be, okay, a really big simplification, right? But just for illustrative purposes, like you would get a return, right, of like 95 cents of that dollar, compared to if it costs, you know, if wind costs the exact same amount to install, let's say it costs $1 for a gigawatt, you would only get 40 cents of the return in terms of like the electricity production. So what this means is when we talk about numbers that have to do with the dollar per megawatt or gigawatt in terms of capacity, you know, if two generating facilities cost the same amount of money, you might still prefer one of those over the other because of how much electricity you know they're going to produce. So this actually becomes an important element of the sort of economic calculation as well. So that's important to keep in mind. Okay, so onshore versus offshore. So the offshore wind capacity, the total amount you can see here. Places like the UK, Germany, China, Denmark have a fairly sort of substantial amount of capacity installed. And then in terms of the growth every year, we can see, again, sort of similar trend. There's not as much offshore wind capacity as there is compared to onshore, right? So we're talking about here on the order of about 20 gigawatt capacity versus, right? In this chart, we can see the total amount of wind is 600. But because of how resource rich this source of energy is, there's definitely a lot of sort of potential growth in offshore area. Okay, any questions about wind? I see, oh, okay, so capacity factor for wind is different on and offshore. Yes, most definitely offshore tends to have way higher capacity factors than onshore. And the wind speeds tend to be quite a bit higher. And so that will also sort of boost the capacity factor. Offshore, we generally consider to be a sort of better resource than onshore, I would say on average, but there are sort of technical challenges and limitations, as well as some sort of political limitations for installing offshore. Like some of the best resources in the United States are offshore in the New England area, but there's like pretty strong opposition to like installing like a wind turbine off the coast of like Cape Cod. It's supposed to be like scenic, right? And so without sort of making judgments about whether that's good or bad, there are definitely there's definitely activism against installation of offshore turbines. As I understand, a lot of that has started to move forward anyways, and so there definitely are wind resources being installed in the sort of New England area. Okay, so continuing onwards, solar power. Okay, so we're gonna see a lot of the same sorts of trends here as we install more photovoltaics. Prices will sort of continue to fall. So you can see prices going from sort of $7.50 per watt, going down to a little under sort of $2 a watt. I think it's starting to approach $1.50 these days. So this, again, this is what I've been mentioning, sort of the levelized cost of energy. This is a way where you can sort of better compare apples to apples based off of, right, because of the differences, as I was just mentioning about costs related to capacity factor. If you actually take all of that into account and make some kind of metric where you can compare them, this is kind of what it would look like. And again, this is actually something that we're gonna cover in terms of how to calculate this in a future lecture, but this will give you some sort of qualitative example of a comparison. So when we look at wind versus natural gas, right, they're pretty close. And solar here is still sort of quite a bit higher and has a lot more sort of uncertainty. Okay, so how does solar work? So we have solar irradiance coming from the sun, and so this energy in the form of radiation is passing through our atmosphere, and there is this sort of general balance that's happening where, you know, some of it is getting reflected back either by air, by clouds, or by the surface. Some of the energy will be absorbed. And then we have outgoing radiation. And some of that will be absorbed in the air and by the atmosphere. But basically the idea is like energy that gets absorbed will get radiated back out, either in the air by the clouds or in the surface. You can see the same sort of thing here. And the whole point is with you know, climate change, you're getting sort of mismatch in the balance between what's coming in versus what's going out, which leads to sort of global heating, and you reach this sort of new equilibrium point, so that you're in sort of a new balance. So the important number to remember is that at the atmosphere, your solar radiation, you're getting about a little more than a kilowatt per meter squared. And by the time that hits the surface of the Earth, what you end up working with is about, I think the number is about 353 watts per meter squared, and that's so 300 to 400 watts per meter squared is the common number that we think about when looking at energy from the sun at the surface. It's gonna fluctuate over the course of the year. And that's because of the amount of stuff essentially that sunlight passes through in the different seasons of the Earth, because it's coming in at an angle, not sort of straight down like you see in this chart. And so the amount of stuff that it passes through is sort of larger in sort of the winter months compared to the summer months. Okay, so atmospheric conditions, time of day, time of year, and solar cycles affect the amount of energy at the Earth's surface. So you're getting about a kilowatt per meter squared coming in, and then accounting for like weather, seasonal variations, averages. The average solar radiation is about 170 watts per meter squared. So in 1 hour, you get about the same amount of solar energy hitting the Earth's surface as all energy consumed by all human activities over a single year. And so if we remember back to one of those earlier figures about the resource availability, you'll remember that like big rectangle on solar energy was the sort of far and away the largest. So from a strict like potential standpoint, yeah, you actually, like if you were to cover the whole globe in solar panels, you could produce more energy than we would ever need in sort of like modern day energy use. But of course, like that's not really a feasible thing to go around covering the entire planet with solar panels. And so we want to think strategically about placements, right? And we want to put solar resources where the resource is the best. So in the US, it looks something like this. This is just sort of a qualitative example, right? So you have highest sort of irradiance in the southwest area. Generally, as you get sort of closer to the equator, you tend to do to get better irradiance. If we look at the entire world, it looks something like this. So, right, the sort of pink is the highest, and then red So again, the sort of Southwest in the US looks the best, but most of the solar potential is sort of best within certain bands around the equator. So our quick sort of similar analogous back of the envelope. Okay, how much solar would we need? We could look at these sort of calculations, installation efficiency, average annual installation. Okay, this is installation refers to the irradiance from sunlight energy and converted. So the area to charge your conventional house might be about the size 100 meters squared, so size of your typical rooftop. The amount to charge your battery car might be slightly smaller. So 20 meters squared, 40 meters squared for hydrogen, just to give you some perspective about relative size needed to provide for particular end use. Okay, so here is our sort of one example so far where we are producing electricity not by kinetic energy in a turbine. So in the case of solar PV, you are not spinning an object. So the way this works is this is a cross section of a solar cell. And essentially what happens is you have a negative and a positive electrode, and as sunlight photons from your sunlight will sort of hit your PV cell. And the energy transfer, essentially, you can think of as kind of like dislodges an electron, right? And so that free electron will want to travel to the positive electrode. And so if you have a completed circuit, that will produce an electric current. Yeah, so these cells are constructed in such a way that you can have this this sort of semiconductor that allows for electricity to flow across this circuit as the electrons are sort of dislodged. And it's done by sort of doping silicon with boron and silicon with phosphorus to produce your positive and negative charges. The highest like lab-based efficiency that we've ever seen is about 46% for solar. But on average, your efficiency for a typical solar array is closer to about 15%. It can be a little bit higher for really good, if you're getting a really good amount of sunlight, but generally it's not much higher than sort of 15%. And so that refers to sort of the relative energy from the solar irradiance compared to the electrical energy that you're getting out of the solar panel. The solar radiation energy that you can get depends on the type of collector. And so when we think about like a photon impacting your solar panel, if it hits the most efficient collection of that energy is if that photon hits perpendicular to the panel. And so that's why during different seasons, you can have different efficiency because of the angle of the sunlight coming in to hit a panel. But it also depends on the type of collector. And so if you see here, like a fixed angle So this is much more common for like rooftop solar, where the panels are kind of sitting at a set angle. You're going to see sort of different like this. So this, if we think of this as like a qualitative amount of energy that you could collect, it might look something like this. But if you have these things like tilt trackers, where you can actually move the panels in such a way that you can move them to be perpendicular to the sunlight energy coming in, you'll actually get higher efficiencies. And so with a tilt axis tracking plate, in the same month, you could get actually more energy.
But that's depending of the season, right?
Yeah, well, okay. So it also depends on the season, because the amount of atmosphere that sunlight travels through is larger during winter months compared to summer months. And so the amount of radiation that arrives at the solar panel is also going to be higher in summer months compared to winter months. So if I looked at this same chart, it would look similar in terms of trend, in terms of availability, or in terms of what you're capturing between these, but then everything will qualitatively be capturing more, because you have more irradiance during summer months. So yeah, season does make a big difference as well. Utility scale versus distributed solar. So we talk about sort of two different levels of solar installation. So this utility scale are these sort of big fields of solar that produce a tremendous amount of electricity. You can think of these as kind of analogous to large power plants, versus distributed solar, which we see at rooftops. These will typically be less efficient than utility scale, right? Because they don't have the tilt tracking technology. You don't want these big things sort of sitting on people's rooftops. But there are certain types of advantages from having it distributed as well. For example, like you can avoid some of the like transmission and distribution losses and that sort of thing. This is one of the rare cases where the energy production happens sort of right at the site of end use. And so for distributed solar, there's this whole scheme of okay, how does that work with the electricity in my home, which I traditionally would be sort of like purchasing from the utility and getting sent to me. So many years ago, they developed this concept of net metering to deal with this. And so if I have rooftop solar on my house, I would take that energy, convert it right from the sun, and then you'd have an inverter. Okay, so the reason why we need this is like with a turbine, you're always producing alternating currents, but with solar energy, you're producing direct current. We won't get into details of power flow and how that works. You can ask me in office hours if you're interested, but you need an inverter. And so instead of pulling electricity from the grid, you're using electricity directly that's being produced from your local resource. And so what you actually end up having is a bi-directional meter. And so this meter you can think of as it measures it measures the quote unquote volume of electricity coming in, but it will also measure the sort of volume of electricity that's getting pushed out back into the grid from your solar panel. And so when your panel is producing power, it's definitely going to be producing more than you could use in any given moment. And so the way that we sort of net that out is by just taking by subtracting the amount that that you're purchasing from the grid versus the amount that you're pushing back into the grid. And so that's net metering. So solar has a number of other applications besides electricity generation. So this is an example of a solar cooker, right, where you can cook food in sort of innovative ways using the energy related to sunlight. Okay, so you might sort of scoff at this and think, okay, well, this is not like that big of a deal compared to, you know, the energy that we're getting from electricity. But in fact, in a lot of like developing countries where a lot of the energy that they use is actually related to cooking. So particularly in lots of places like Africa, certain African countries where you have like wooden cook stoves, this actually represents a really important technology for time, energy, and monetary savings. There are certain places where a lot of a person's effort might be going into sort of collecting fuel or purchasing fuel in order to do something like you know, cooking hot meals. And so this represents a technology that can provide tremendous savings for certain populations in developing countries. Solar heating systems are also are an efficient way of saving energy. And so this, you can, if you've ever seen these sort of like black tarp-like materials on people's rooftops, these are solar, so they're called solar collectors, essentially, where you run water through them to heat it up. And so that goes into these water tanks. And so the idea isn't that, okay, so in your typical apartment or house or something, you're going to have this hot water tank, and that tank is kept hot so that you have hot water available to you at any given time. And that actually uses a tremendous amount of energy, because heating water takes a lot of energy. And it's not as though the solar energy is necessarily hot enough to bring that water to the temperature that you traditionally get in a water heater, but it is warm enough to bring the temperature of water up higher, so that the amount of energy that you need to get the last bit of temperature differential up is a lot lower. And so these are actually tremendously efficient systems that potentially can save quite a bit of money for folks who use hot water. Another different form of solar energy, so this is one that I mentioned earlier, is concentrated solar power. You know, I was saying solar power doesn't use turbines, but that's not quite true. So photovoltaic doesn't use turbines, but you know, that's the kind of technology that we're sort of used to and have developed over you know, a century now. And so someone thought up of the idea to employ that in solar power as well. And so the way this works is you have these large facilities that have all these mirrors, these sort of concentric mirrors that will take sunlight and reflect it to a specific point. And so this ends up, you're not actually using solar panels, and therefore I believe this, some parts of the technology can end up being cheaper than photovoltaic. But the basic idea is all of these mirrors will reflect the sunlight to a specific point, and this receiver will essentially heat up water, and then you've got yourself a nice steam turbine, same as you would for nuclear power or for coal plants. And you use that heated water in the same fashion to generate electricity through a steam turbine. This is not a super common technology. It's used a lot in Spain, and there are some instances of CSP in the United States. There's a few installations of these in like desert facilities in California, for example, but a very small amount, so 5 gigawatts total in terms of the CSP technology. Okay, decentralized versus centralized. How much rooftop solar do we have versus the utility size solar? So we can see in yellow, this is the utility scale, and then in the orange is your sort of more distributed, like rooftop solar types of installation. And so the share has definitely moved more towards utility scale over time, but this is just sort of percentage of capacity. In terms of total capacity, we see growth across both installations pretty consistently. Okay, going back to this total accounting of renewable energy, about 18% of global final energy in 2017. And so that's sort of all types of energy. And then for electricity specifically, it's closer to about a quarter of electricity production. And again, just a breakdown, in electricity, you've got hydropower as the bulk, followed by wind, and then followed by solar and biopower. Okay, I have a couple more slides on sort of environmental impacts of renewables, but I think what we'll do is we'll just pick up with that on Thursday, so I don't go over time here. And so we'll finish off the last couple slides on environmental impacts next class. So in the meantime, yeah, we'll end for today. Take note that the homework is going to be posted shortly, and that'll be due again next Thursday. I'll stick around a couple minutes for any questions folks may have. Otherwise, I'll see you guys in 2 days.
For the homework,